Hi, in this seminar we will be talking about parallelism.
No, I'm just kidding. This is not gonna be that type of seminar because, well, we all hate that kind of voice, right? So, okay, we are gonna talk about parallel computing. I hope that my explanations are pretty clear. I really tried my best so that you guys could understand these complex concept. And well, why parallel computing? Because yeah, the shift in computing hardware to parallel systems is well underway. So that means that sequential chips are no longer designed, and the proud era of von Neumann architecture passes into history. So that means that foundational change of this magnitude will disrupt traditional habits throughout the discipline, especially how students, us, are to be introduced to and prepared for new challenges. But prepared how and for what exactly? So yeah, with problem programming models evolving and a variety of approaches being tried in academia and industry, this means that flexibility is vital. So customary time lags between research findings and classroom experience will have to be shortened so that we can have the industry experience when we get to work, right? So, okay, in this presentation, I'm gonna have a lot of analogies because I think this makes everything easier to understand. So yes, analogies everywhere. So just be prepared. Before explaining what parallel computing is, it's really important to know what serial computing is about, because since the very beginning, software has been written for serial computation. And what is serial computation? So this means that a problem is broken into a discrete series of instructions. Instructions are executed sequentially one after another, just like in this example where we have instruction A, B, and C. And instruction A is going to be executed first, then after it finishes, instruction B is going to be executed, and at last, after instruction A and B get executed, C is going to start being executed. So of course, all of these instructions get executed on a single processor because of course only one instruction may execute at any moment in time with this processor. So let's have a really quick example in which let's assume that we're in a company where we have to calculate the payroll for our employees. So in order to calculate the payroll for this company, a software that employs serial computing would first do the payroll for employee number one, then for number two, and so on and so forth until the nth employee gets its payroll after the n minus one employee gets its payroll. So yes, this must be done sequentially, one after the other. And of course, this takes a lot of time, assuming we have, I don't know, a million employees. This would be so computational expensive. So, okay, now that we know what serial computing is, well, what is parallel computing about? In the simplest sense, parallel computing is the simultaneous use of multiple compute resources to solve a problem. Using the same examples as before, let's assume that we have instruction A and B, and yes, what we have in parallel computing is that instead that B gets executed after A finishes, A and B are executed simultaneously at the same time. Yes, so a problem is broken into discrete parts that can be solved concurrently. And I want to just make a distinction between parallel and concurrency. Parallelism and concurrency are similar concepts, but they are different, and I'm going to talk about that in the next slide. So each part is further broken down to a series of instructions. Instructions from each part execute simultaneously on different processors. And of course, a neural control coordination mechanism must be employed so that this parallelism can be executed. So using the same payroll example, a software that would employ parallel computing would first calculate the n employees' payroll simultaneously, rather than having to wait for n minus 1 payroll calculations in order to calculate the nth payroll, just like happened in serial computing. So given this definition of parallelism, it is important that the computational problem that we are trying to solve can be broken apart into discrete pieces of work that can be solved simultaneously, so that the multiple prime instructions can be executed at any moment in time. So this means, of course, that the problem will be solved in less time because it will use multiple compute resources rather than if we had just a single compute resource. And of course, a compute resource can mean from a single computer with multiprocessors or cores, or an arbitrary number of such computers connected by a network. And I'm going to talk about this in a few more minutes. So, okay, remember that I said something about concurrency? Yes, it's really important to take a grasp on these concepts, parallelism and concurrency, because yes, they are two related, but they are distinct concepts. Why? Concurrency is about dealing with lots of things at once, while parallelism is about doing with lots of things at once. So yes, I mean, this is really important to know, because one is about structure and one is about execution. So let's have our first analogy of the presentation. Let's say that we have a mouse, a keyboard, and a display. All of these tasks are being executed at the same time in the computer, and we think that they are being executed at the same time, but in fact what happens is that the operating system is just giving a slice of time to each job, and this slice of time is so small that we think, I mean, this time is so imperceptible to us that we think that all is being executed simultaneously, but in fact it just making a loop between these slices so that every device gets its own time, and this happens concurrently. And well, the parallelism analogy is, well, let's imagine that we have a task of ordering a shuffle deck of cards by suit and then by rank, and how would it be, what would be the best way to do this? Of course, it would be faster if the task is carried out by two or more people, because by splitting up the decks and performing the instructions simultaneously, then at the end, combining the partial solutions, we could say that we perform a parallel computation, and this took a lot of less time than if just one person made it. So moving on to why is parallelism so important? That's because the end of the uniprocessor era was like 10 years, 12 years ago. And yes, Intel canceled its high performance uniprocessor a lot of time ago, and since then all of our computers are multi-cores, and this is a big deal for us computer software engineers to make software that is able to perform to perform with parallel algorithms, so we can use all of the available resources that we have. So why use parallel computing anyway? Well, that's a really good question. The real world is actually parallel. This is really important because in the natural world, many complex interrelated events are happening at the same time, yet within a temporal sequence. Compared to serial computing, this means that parallel computing is much better suited for modeling, simulating, and understanding complex real-world phenomena. So we can see that this modeling can be done in climate change, planetary movements, galaxy formation, and even weather. So yes, the nature is parallel, and we must adapt ourselves so that we can get all of the information processed in a good way. So who is using parallel computing? Historically, actually, parallel computing has been considered to be the high end of computing and has been used to model difficult problems in many areas of science and engineering. From atmosphere, earth, environment, physics, bioscience, biotechnology, genetics, mathematics, and we could even ask the USA what they think about parallel computing when they use it for defense weapons. Of course, it is used in this sense. So yes, parallel computing is used in a lot of areas, and we can see that in this graph. I find it really interesting that there's an other other area which englobes a lot of things that I'm not really sure about. I actually looked about it, but couldn't find info. But we can see that a lot of application. I mean, parallelism is used a lot in research, and that was like historically has been used in research, but this has changed a lot and we can see now that it is used in services, in finance, in defense, like I was saying a minute ago, and of course it is important. Parallelism is really important. So moving on to commercial applications, it is also used in this sense. For example, in data mining and databases. And something really cool about it, I found it, that MapReduce is a programming model for processing and generating large data sets with a parallel distributed algorithm on a cluster. And Google, for example, uses this programming model for indexing its searches. So that's really cool. If you wanna research more about it, just Google Hadoop, and you will get a grasp on how to program using this programming model. So okay, back to our presentation. What are the types of parallelism in software? We have 4 types. And actually the transaction level parallelism is not that important, so I'm just going to focus in instruction level parallelism, ILP, thread level or task level parallelism, or TLP for short, and data level parallelism. So yes, the number of types of parallelism is not too damn high, but you get a sense that we have they're not that, I mean, yes, they are kind of high. So okay, before explaining these 3 concepts, it's really important to know what pipelining is, because it is like the foundation of everything in parallelism. So pipelining is an implementation technique where multiple instructions are overlapped in execution. The computer pipeline is divided in stages. Each stage completes a part of an instruction in parallel. And of course, these stages are connected one to the next to form a pipe. That's why it's called pipelining. The instructions enter at one end, progress through the stages, then exit at the other end. So pipelining does not decrease the time for individual instruction execution. Instead, it increases throughput. The throughput of the instruction pipeline is determined by how often an instruction exits the pipeline. So yes, the thing with pipelining is that it can overlap the execution instructions when they are independent of one another. This potential overlap among instructions is called instruction level parallelism, ILP, since the instructions can be evaluated in parallel. So ILP takes advantage of sequences of instructions that require different functional units, such as load unit, ALU, FP multiplier, etc. The idea is to have these non-dependent instructions executing simultaneously to keep the functional units busy as often as possible. Say what? Yes, this can be explained in a simple example. Let's say that we have these three operations: E equals A plus B, F equals C plus E, G equals E times F. Of course, we can see that operation 3 depends on the results of operations 1 and 2. So it cannot be calculated until both of them are completed. However, we can see that operations 1 and 2 do not depend on any other operation, so they can be calculated simultaneously. If we assume that each operation can be completed in 1 unit of time, then these 3 instructions can be completed in just 2 units of time. So the goal of the compiler in ILP and the processor designers is to identify and take advantage of as much ILP as possible. Ordinary programs are typically written under a sequential execution model where instructions execute one after the other and in the order specified by the programmer. And in this sense, we have to adapt our compiler so that the sequential instructions can be used by the processor in a parallel way. Moving on to the next type of parallelism, we have a thread level parallelism, or TLP for short. TLP is the act of running multiple flows of execution of a single process simultaneously. TLP is most often found in applications that need to run independent, unrelated tasks, such as computing, memory access, and I/O simultaneously. And it's really interesting that this type of applications are found on a machine that have a high workload, such as web servers. And yes, multiple threads or instruction sequences from the same application can be executed concurrently, and they're often generated by compiler or by the programmer and managed by the compiler and hardware. Moving on to the next one, which is actually really important, is the data level parallelism, or DLP for short. DLP is the act of performing the same operation on multiple data simultaneously. For example, an operation on an image in which processing each pixel is independent from the one surrounding, such as brightening. This can be done in a parallel way because each pixel is independent and they do not depend from the others. And actually this is closely related to an SIMD machine, which executes a single instruction on multiple data values simultaneously using many processors. But don't worry, this will be explained with more detail as we go further into the video. So yes, let's have an example of what DLP is. Let's say that we have two arrays and we want to add them, and this can be done simultaneously if we add the first indexes at the same time, then the second indexes at the same time, and all at the same time, the 3 indexes plus the other 3 indexes, and do that in 1 unit of time, because they do not depend on the indexes do not depend on the other ones. So yes, and let's have another analogy. Let's say that we want to prepare food for several banquets, and each of which requires many dinners. We have 2 positions: one boss, lots of chefs. And what would ILP be analogous to? It would be analogous to one ultra-talented boss with many hands, or one ultra-talented chef with many hands. TLP is analogous to building multiple kitchens, each with a boss and a chef, putting more bosses and chefs in the same kitchen, and final DLP is analogous to one boss and lots of chefs. And well, although I didn't explain a lot of transactional level transactional level parallelism, I'm just gonna talk really quick about it. It is like having multiple threads and processes from different transactions to be executed concurrently, and it is limited by access to metadata and by interconnection bandwidth. So yes, that's the thing about transactional level parallelism. Like I said a few minutes ago, it is not that important. The most important ones are these three, and I just explained them. So okay, so moving on to the types of parallelism hardware, it's pretty straightforward. We have shared memory multiprocessors, distributed memory multiprocessors, and chip multiprocessors, or multicores for short. So yes, before explaining all of these hardwares, let's take a look at what the Flint's classification is, because this classification was first studied and proposed by Michael Flint in 1972, and this was an era where parallel computers didn't exist, and there was no idea of this concept. So because of this, he introduced the concept of instruction and data streams for categorizing the computers, and based on this idea, the parallel computers were made. So that's why it's really important to take a look at this slide. So it's pretty straightforward. We have four types in the Flint's classification. The last one is not that important. So I'm just going to talk about the single instruction, single data stream. SISD machines, for short, execute a single instruction on individual values. And therefore, SISD machines are conventional serial computers that process only one stream of instructions and one stream of data. So they're pretty straightforward machines. They're really simple. And yes, the next one is SIMD, single instruction, multiple data stream. SIMD machines execute a single instruction on multiple data values using many processors. So since there is only one instruction, each processor does not have to fetch and decode each instruction. Therefore, all the processing elements simultaneously execute the same instruction and are said to be lockstep together. The next one is MIMD, the multiple instruction, multiple data stream. These are the parallel computers that we have nowadays. MIMD machines execute multiple instructions simultaneously, and they may execute multiple instructions simultaneously, contrary to SIMD machines. And of course, each processor must include its own control unit that will assign to the processor parts of a task or a separate task. And therefore, for handling multiple instruction streams and single data stream, multiple control units and multiple processing elements are organized in this classification. And the last one is not that important, so let's not care about it. Okay, let's have another analogy. Let's say that we have a check-in desk at an airport, and SSID would be analogous to having a single desk. SIMD would be analogous to having many desks and a supervisor with a megaphone giving instructions that every desk obeys. And finally, MIMD would be like having many desks working at their own pace, synchronized through a central database. So back on track, shared address, remember what we had in here, the shared memory multiprocessors. Before explaining the Flint's classification, we have these three types of parallelism hardware. So yes, shared address or shared memory is processed in different processors can use the same virtual address. Any processor can directly access memory in another processor node, and communication is done through shared memory variables. So in this way, shared memory address is really easier to program than the other type, which is message passing. So let's take a look at what message passing is. Message passing is is like having processes in different processors use different virtual address spaces, contrary to using the same virtual address in shared memory. Each processor can only directly access memory in its own node, contrary to shared address or shared memory, in which any processor can directly access memory in another processor node. So communication, of course, is done through explicit messages, whilst in shared memory is done through shared memory variables. So in this way, yes, it's arguably harder to program. So what is the uniform memory access? It is a type of shared memory addressing, and it is most commonly known as asymmetric multiprocessor machines, SMP machines, in which there are identical processors and they'll have equal access times to memory. And what's the other type? The other type is non-uniform memory access, the NUMA for short, and it is often made by physically linking two or more SMPs. One SMP can directly access memory of another SMP. Yes, it is a shared memory addressing type. And the thing here is that we have a bus interconnect that links each of the SMPs. In distributed memory, systems require a communication network to interconnect memory, and processors have their own local memory operated independently. In this case, it is message passing type of addressing. And of course, there are these 4 SMPs, and they are interconnected by a network, typically Ethernet. So of course, there's this bandwidth limit of information transfer. Moving on to our last concepts, there's this thing of decomposing data and tasks. It is really important to decompose in our parallel algorithms data and tasks. And for data, we identify first the data in which computations are performed. We partition data into subunits, and data can be input, output, or intermediate for different computations. For tasks, a given problem may decompose into tasks in many different ways. Tasks may be of the same, different, or even in determinate sizes. What is deadlock? Deadlock is really straightforward. I think that we saw this in our systems operating class, but pretty much is when a resource is waiting for another. I mean, a job is, well, when 2 jobs or tasks are sharing the same resource, are effectively preventing each other from accessing this resource, resulting in both programs ceasing to function because A is waiting for B to finish and B is waiting for A to finish, and this never ends. So how can we avoid this? By using multiple exclusions. There are 2 approaches: the semaphore way and the monitors way. Semaphores are implemented in the system kernel. Monitors, they are implemented in the programming language. And synchronization is another really important thing when we use a thread level, when we use a TLP. In the C language and in the Java language, we have the fork and join thread method. The join method would be the synchronization way of joining of handshaking all of our multiple processes at a certain point, so that they all reach an agreement to commit to a certain sequence action. So what are the programming languages that support parallelism? We have Erlang, C, C++, Haskell, and Java. C and C++ support parallelism when we include some libraries like OpenMP library. So how can we measure performance? Throughout using turnaround, the sum of the total waiting time and execution time, and throughput, the total amount of work done in a unit of time. this we saw this in our operating systems class, so it's really easy. I know that you guys know it. So thank you very much for your attention. I hope that you can understand everything. See ya.